Hello and welcome to another course on antenna theory, waves, and microwave communications. Now this course will be almost a complete one. It shall cover multiple subjects starting from antenna theory, propagation, fading problems or propagation problems, etc. Actually, we're going to see the schedule that was established for this course on the next page. So at first, we have frequency spectrum used for telecommunications, propagation principles, propagation problems such as fading, attenuation, and absorption, Maxwell's equations, a little bit overview on that, antenna beam, gain, and radiation pattern, which are the different parameters, critical parameters for the antennas, propagation zones, including Fresnel, Fraunhofer, and Rayleigh, antenna design criterias, antenna parameters and equations, transmission circuit, or a block schema, if you will, dish antenna, and finally microwave communications. So let's get started. At first, the frequency spectrum refers to the entire range of the electromagnetic wave frequencies used for transmitting data, for telecommunications and transmission. Transmitting data over the air, through cables, or via optical fibers. Of course, optical fibers use nanometric waves which are in the visible range. It spans from very low frequencies like VLF, very low frequencies, up to extremely high frequencies, EHF, and beyond into light waves. So starting from extremely low frequencies, less than 3 Hz, they are used for submarine communications and seismic studies. Given they have lower frequencies, so longer wavelengths, they can penetrate deeper underneath the earth and in different, rock formations within the ocean. SLF, super low frequency, 3 to 30 Hertz for submarine communications as well. ULF, or ultra low frequency, 3300 Hertz, for geological surveys. VLF, okay, very low frequencies, ultra low frequencies, yeah. They are flipped here. This is very low frequency, 3 to 30 kilohertz for maritime navigation, all the way to UHF, ultra high frequencies for TV, mobile phones, and GPS applications. All right, so for higher frequencies, you can carry higher capacity, but the range would be shorter. That's the difference mainly between longer frequencies or longer waves and shorter waves. Shorter waves have higher frequencies, so they can carry higher capacity for data, but longer wavelengths, shorter frequencies, they have higher penetration. They can go through thicker obstacles, so their range would be longer or greater. So also another two wave bands, SHF or super high frequency, 3 to 30 gigahertz radar, satellite, Wi-Fi, microwave, or EHF, extremely high frequency, used for 5G, radio astronomy, and high frequency radar. Propagation principles. For a wave to go through an obstacle without any significant attenuation, its wavelength needs to go or to be greater than or equal to the thickness of the obstacle. So lambda, in other words, should be greater than and equal to the thickness of the barrier it's going through. The consequence of that is that lower frequencies, of course, which are longer wavelengths, would have a higher range, travel further with a longer range, and can penetrate thicker obstacles such as walls and buildings without any significant attenuation. On the other hand, higher frequencies are more prone to absorption and attenuation, so they have a shorter range because due to the free space loss, even within the atmosphere, they can attenuate drastically after high distances or long distances. So they have a shorter range and don't have the ability to penetrate thicker obstacles. For instance, microwaves need to have a clear line of sight, a path without any obstruction in clear sky to reach destination without the signal's amplitude dying prematurely. As for the bandwidths, longer wavelengths, due to their lower number of oscillations of these peaks per second, carry low data rate. Why? Because data is modulated on either the amplitude, the peak, or the trough of each wavelength, of each oscillation, or the phase, which is the angle within the signal. All right, but shorter wavelengths of a higher frequency can carry a larger amount of data. Why? Because they have a much numerous, a larger number for different oscillations, for different peaks, so they can carry a larger amount of data. As a result, for that, greater bandwidths can be carried through higher frequencies due to their higher number of peaks, of oscillations, of wavelets within the signal during each second. So as we noticed in the first slide, the application of very low and ultra low frequencies is for geological and marine explorations, given their ability to go through thick layers of either soil, rocks, or water. That's why we use these extremely low frequencies for such applications, and to return back to the receptor due to their very long wavelengths. As for higher frequencies, they are more susceptible, way more susceptible to obstacles, especially ultra high frequencies. Their application involve a clear path freed from any type of obstacle, for even trees have the ability to block the signal in such case, and even bad weathers involving having rains can enormously absorb and attenuate their signal's intensity. To give some examples on where different bands are applied, VHF and UHF are used for broadcasting AM, FM, radio, and TV. Wireless communications such as mobile and Wi-Fi use UHF and SHF because you need a high data rate to be transmitted. Attenuation. Okay, let's start with propagation problems. So you have, first of all, the attenuation. The attenuation problem of the wave's amplitude is due to multiple factors contributing to the flux density absorption, which is the flux being the intensity of the electromagnetic field within or per meter square of area. So this includes obstacles such as walls, buildings, mountains, and other ambient objects or surrounding objects. All of these factors lead to a uniform decay or degradation of the signal's power that's being received on the other end. So yeah, by the receiver. Another contributor to that phenomena is the increased distance between the transmitter and the receiver, which, by the way, here we call it free space loss. So even without obstacles, the free space loss is the loss of the power of the signal within free space, even when there are no obstacles available, even when considering rain or fog or vapor, water vapor being obstacles. But even in free space, you have a gradual attenuation of the signal. The wave absorption by the atmospheric layers is given by the following formula, which is delta equal AN times nu times delta L divided by the frequency squared. A being what's called the proportionality coefficient. N is the density of electrons here. Nu is the number of electronic collisions with neutral charges during 1 second of a time. And delta L being the distance traveled by the signal. So, of course, F being the frequency value, the frequency of the signal itself. But here you have a clear proportionality or a clear relationship, direct relationship, which is proportional between the atmospheric absorption and the delta L, which is the distance being traveled by the signal. And we also, at the same time, notice how the absorption is inversely proportional to the frequency, which for some doesn't make any sense, okay? Meaning that for higher frequencies, we get a smaller absorption. Why? Now here we should not confuse the concept of absorption with attenuation. Okay, they are two a little bit different concepts. Okay, absorption means that, for longer wavelengths, the absorption is higher, meaning that you have a what starts to happen is the refraction, okay, gets more severe, the refraction of the signal. That's one way to look at it. Plus, lower frequencies have lower energy to go through the atmospheric layers, all right? So they would be reflected back. That's why, by the way, you have, for a signal to go from the land to the satellite, it needs to at least have a frequency of 36 megahertz. That's the critical minimum frequency for it to go through the atmosphere without being reflected back due to gradual refractions. And what would happen for lower frequencies is that the signal would be reflected back from the ionosphere, which is, you know, an ionized, like a metal sheet, if you will, layer within the atmosphere that reflects the signal back to Earth. So for higher frequencies, you have higher energy for a wave and lesser absorption, so it can go through and penetrate without being, you know, it will be attenuated, of course, but it won't be fully absorbed by the atmospheric layers due to its higher energy having a higher frequency. Another problem, which is fading. Now, fading by definition is the sudden fluctuation in the intensity of the signal as it's being received by a receiving antenna. Multiple factors contribute to that phenomena as well, among which the shift of the height in the ionosphere layer, which is the metallized, if you will, the ionized layer of the atmosphere. So as it shifts upward during the night especially, this layer of the atmosphere, given that it is charged and ionized, acting like a metallic reflector, this will also affect the intensity of the signal being reflected from up that layer, from the upper atmosphere. So other factors are cosmic radiations and sun flares, the increase of the Earth's temperature during the day, and magnetic storms caused by the surface of the sun. So these can lead to intense ejection of ultraviolet and X-ray radiations with a high photonic density, interfering with the signal. So magnetic sunstorms can perturbate radioelectric transmissions on the Earth, and they can persist for weeks, affecting every electronic device, especially high altitude satellites, radars, and other communication devices on Earth. As the sudden magnetic fluctuations given due to their effects, what happens is that they create a parasitic adverse inducted current in these devices. Plus, you know, that swapping, that fluctuating electromagnetic field would affect any transmission outside of the device. That's why we get what is called, you know, the fading. You see here, the fading, as mentioned, is the sudden fluctuation of the intensity of the signal, and it can happen in different areas randomly, meaning in different times for different frequencies. So it's not frequency related. It can happen randomly, and it doesn't happen at the same time for the same frequency. So it has a randomness, and it's not frequency related. Rayleigh fading. Another type of fading is the Rayleigh fading. So this fading type occurs when multiple obstacles are at the proximity of the receiving antenna, which causes the signal to be reflected and sent from different paths following different asymmetric trajectories back to the receivers. So you have multipath fading. Multiple versions of the signal had traveled a different distance, including the wave that is received directly. What happens in such case is that different versions of the same signal having the same power are arriving at different times, meaning they are out of phase. All right, at different times, the timing affects the phase of the signal. So some will be constructive, building up, adding up. Some will be destructive, as you see in this second illustration to the right. The phase is 180 degrees. Now, 180 degrees means this is how damaging it is. You know, a shift of half of the wavelengths to the right, okay? Or, you know, the green one is the one that had arrived late. So you see, if you add these two signals, these are the same signals shifted by 180 degrees. If you add them together, having the same frequency, they annihilate each other, meaning that the sum resulting sum of the signal would be 0. Why? You have on one part you have plus, on the other you have minus. So they annihilate each other. Time dispersion. This phenomenon occurs when the receiver gets two signals, one coming directly from the source and the other having been reflected by an obstacle that is sitting at a much further distance due to the large time delay between the two. Okay, so the second signal interferes with the next transmission that follows the first signal. Okay, so it's actually arriving at the timing, almost at the timing of the second signal. So what happens is that both the original signal, both the next transmission, the next signal, and the original signal that is arriving after a long delay, they mix up with each other. So you have a binary mix-up. The bits mix up together, and the receiver won't arrive to decide which reception or which bits are correct and which are not. Okay, that's the problem here. So you have one signal that has been reflected from a far obstacle arriving back to the receiver, and it's kind of, being received during the time or at the tail of the first transmission. Okay, it's mixing up with the first version of the signal arriving directly. This is what causes the errors or binary errors and the mix-up of bits, where the receiver can no longer decide which version is correct. Time alignment. Time alignment is a familiar problem with mobile network communications, and this is when it takes too long for a signal to attain the receiver that a time frame, which is using TDMA, time division multiplex access, especially in the older GSM network, by the way, it will arrive right at the timing, so it will coincide with the arrival of the next frame. So you have, this was supposed to be received first, okay, but another version from it has been reflected from a far obstacle, so it comes back to the receiver and it aligns, it coincides with the same timing of the second frame. Okay, so you have two different communications at the same time. Okay, two different frames being received at the same time instead of one. That's why these two aligned frames, okay, they are mixed up together due to that, and due to the fact that one of them had arrived late from a far obstacle. That's the problem. Of course, you have different mechanisms to cope with this problem and to rectify this error. Okay, Maxwell's equations. Now, coming to the antenna theory, let's talk about Maxwell's equations that are, the contributors to electrical or electronic transmission. Okay, so Maxwell's equations are a set of formulas that describe the interactions of electrical and magnetic fields depending on the propagation path and other environmental and operational factors. So let's first start with Gauss's law for electricity. So at first you have delta E, actually this is nabla. It's called, another Greek symbol. Nabla E is equal to rho divided by epsilon 0. Here, what this law means that the electrical flux within an area is proportional to the total electrical charge enclosed inside that area. Rho, by the way, being the charge density divided by relative permittivity of empty space. Okay, and here nabla E means it's the divergence of the electrical field. So it's actually, the derivation of different coordinates of the electrical field, different vectors, okay, which gives us the power of the signal, or the flux, the total electric flux of the signal. Okay, when you derive, you're getting the amplitude, the power of a signal, of a curve, right? Gauss's law for magnetism. Another law is Gauss's law for magnetism, which states that there are no magnetic monopoles. Actually, the entire the sum of all magnetic field is 0. Why? Because any northern field is counteracted with a southern magnetic fields, which renders the entire or the overall magnetic field within an area is equal to 0. Why? Because it's countered by a southern pole. That's why when you have a north and the south, they pull against each other. So there's no actually a one-way magnetic intensity. There's a loop that renders the overall magnetic field, okay, the divergence of the entire magnetic field would be 0. The overall intensity of the field itself. Third, Faraday's induction law, which states that a changing magnetic field, okay, here you see the derivation or like the partial of B being the magnetic field during a certain or like a duration of time, a time span. This change of the magnetic field during the time variable would also imply a change of the electrical field. So they are connected, or they are directly related to each other. A change of the magnetic field would also lead to a change of the electrical field. Okay, so they go hand in hand, in other words. Ampere's law with Maxwell correction. Okay, so here what we're saying within this equation, and this was done by Maxwell. So the curl of the magnetic field, which is also, the variation of the magnetic field, is equal to the magnetic permeability, this is mu0, multiplied by the current density, the density of the electrical current, plus permeability 0, epsilon 0, which is permittivity 0, both in empty space, this is why it's 0, multiplied by the fluctuation or the change, the derivation of the electrical field during time. So what is happening, it's the same concept, but it's like an extended formula. The change of the magnetic field is interrelated or connected to the change of the electrical field multiplied by mu0, which is magnetic permeability in empty space, and epsilon 0, which is the permittive or permittivity, electrical permittivity, plus the current density multiplied by mu0 as well. Now going to the antenna beam and the radiation pattern. So first of all, the shape of the beam projecting from an antenna has a unique form, a unique, if you will, shape, okay, or anatomy. There are three main types of lobes projected from an antenna. Not only one type, not only one projection. You have three types. First, you have the main or primary lobe, which is the main beam pointed in the same intended direction of the transmission, in the same intended radiation direction. It is where most of the power of the radiation is concentrated, and this is what we focus on doing. We try to make this main lobe, okay, as large as possible in a way to reduce the other lobes. This is where we know why. So, because this main lobe is the only one taken into account when measuring antenna gain and directivity. This is the useful radiated beam, okay? The part of waves that are being used for the transmission and the communication are the ones belonging to the main lobe. Next, the side lobes. Side lobes are parts of the main beam scattered sideways, and they represent wasted radiated power for the antenna because they are not taken into account, like they are not directed intentionally in the same heading of the transmission or the communication. They are side lobes, they are like collateral damage, so to speak. So they spread in a different direction than the intended radiated path. More than that, not only they are a wasted power and energy, but they can interfere with other antennas and communications coming from other transmission stations that happen to either use the same frequency or a closer frequency than that. Finally, you have the back lobes. The back lobe, also considered a scattered and wasted energy, except, this lobe points to the opposite direction. That's the difference between itself and the side lobes. Its effect is more prominent when we have back-to-back microwave antennas in a chain topology. Why? Because this back lobe would interfere directly with the antenna mounted on the back of the other on a chain topology in microwave. That's why in microwave, for two antennas mounted back-to-back, okay, sideways, each one would need to have or to use a very different frequency than the other, okay, to eliminate the problem of interference. By the way, between P1 and P2, that would be, if you will, the bandwidth at -3 decibels, but we'll get to that later. Now, what is directivity? Directivity is the concentration of the power of the signal in the main radiation direction. It is evaluated by how many times a directive antenna, you see, in the main lobe, outruns or outshoots an isotropic antenna, which is a theoretical antenna that radiates the same power uniformly in all directions, okay? Again, it's a theoretical version of the antenna, okay? But this is how we measure the directivity of a specifically catered practical antenna, okay? So, again, the main or the directivity is evaluated by how many times a directive antenna outruns an isotropic antenna, radiating the same power uniformly in all directions, transmitting at the same power again, same conditions of propagation, meaning same temperature, weather factors, same air pressure, also the same frequency, operating at the same frequency. So this is the measurement of the radiation pattern. Okay, so looking here at this observation or this illustration. So this is the directive antenna, and if we measure or plot an isotropic antenna, meaning in other words, if this directive antenna was considered or was designed in a way that was isotropic, it would have this beam projected in all directions, okay? It would be the isotropic version of it, working at the same power, transmitting in the same weather conditions, weather factors, and working at the same frequency, would have this intensity of the signal going, to the first squadron, in other words, to the first, square, to the first distance. So the directivity, which is the difference between the directive antenna, the primary lobe of the directive antenna, okay, which is, by the way, the intensity of the signal going in that direction, and that, which is, by the way, concentration of the power of the signal again, going in that direction, and the signal or the intensity of the signal for the isotropic version, okay, in such case, if you measure the difference between those, you have, for the main lobe, 3 quarters have been, if you will, trespassed, overrun, and for the isotropic antenna, you have only one square, one circle. So, thus, the directivity in such case is equal to 3, or if you will, it's 4 minus 2. Here you have 2 circles going from the center all the way to the isotropic antenna. So you have 4 circles, 4 distances, minus 2, which gives us 2. That would be the directivity of this directional antenna. The gain. So what is the gain? Antenna's gain is actually a relationship between the surface of the antenna, which is the part that reflects the signal from within the inner part of a dish antenna, for example. That's the inner skin of the plate. And that is a relationship between that area, the gain, and the wavelengths, okay? And the surface, all related together. So G equal 4 pi SEF, meaning the effective surface of the antenna, divided by lambda square, lambda being the wavelengths. Now, the effective surface is equal to the geometric surface times nu. Nu is the antenna surface utilization factor, because there's no way you're gonna have 100% utilization of the surface area for a dish antenna or any other types of antenna. There's always waste. First of all, as a parabola shape, it's only a section for a dish antenna. It's not the entire parabola, as we know, okay? Second of all, this is due to manufacturing imperfections. You know, there is no such thing as 100% reflectivity of a metal for a radio signal. So G or D is the gain of directivity measured in the CBOS. Effective surface is the surface which is, you know, around 60% of the area, the entire inner area of the antenna, that's actually reflecting the incoming waves back to the receiver, mounted on the focal point, because, you know, the dish is reflecting the signal back to the receiving point, the receiving device mounted on the foci of this parabola. So, and as we notice that the directivity gain is proportional to the area of the antenna. You see, they are directly proportional, meaning that for a larger or for larger antennas, we would have a narrower, more focused beam versus a more curvy, blobby one. But it is inversely proportional to lambda, which is the wavelength. So in other words, for longer wavelengths, you would have a more, you know, lower gain and a wider lobe, instead a more focused parallel beam, a tubular beam. So for shorter wavelengths or higher frequencies, you would have a higher gain, because wavelengths is inversely proportional to the gain of directivity, which means for longer wavelengths, you would have a wider beam, not focused or laser. That's why, by the way, lasers are, you know, very linear signals. The beam is very linear, is very focused, like a tube, like almost like a line. Why? Because lasers are very high frequency signals. They are very high frequencies. They operate at a very shorter wavelength. That's the secret behind them. All right, so we know that V equal lambda F, lambda equal, yeah, wavelengths and frequency are inversely proportional. That's the point here. Propagation zones. So let's start with the first zone, because, you know, a wave propagation path can be broken down to three major zones. Let's talk about them. At first, relay zone, it extends from the antenna, the transmitter, all the way to a distance of d squared divided by 2 lambda, d being the directivity gain of directivity in the CBOS, and lambda is the wavelength. All right? So within that area, all the rays, all the waves of a beam would be, you know, all the vectors, if you will, are parallel to each other. There's no specific or there's no serious deflection from these waves. You have a parallel, perfect beam, actually, up to d squared divided by 2 lambda. And the main spectral density is kept within that tubular beam. Now, beyond that, within Fresnel zone, which extends from d squared over 2 lambda up to 2d squared over lambda. This is the span of the Fresnel zone. Again, d being the gain of directivity and lambda is the wavelength. So within that zone, you have 80% of the power of the signal is, you know, concentrated. Plus, within that signal, you know, the signal starts curving from the main parallel flow. Okay, so it starts diverging. The main wave vectors are no longer perfectly parallel to each other, unlike relay zone. Okay, so the signal vectors start gradually diverging from the main path. That zone, by the way, should be cleared. It's very critical and important for this zone to be cleared from any obstacle. That's Fresnel zone that carries 80% of the signal, of the power of the signal. So there should be no obstacle, and there should be a line of sight between two communicating points within that area. Finally, Fraunhofer zone, which is the zone above the distance of 2d squared over lambda. This is the zone extending beyond 2d squared divided by lambda, meaning after Fresnel zone. Here, in this area, the radiation vectors are no longer trustworthy, so to speak. They start curving away dramatically from the main beam, and they can no longer be counted upon for a reliable transmission. Why? Because we start having a very drastic divergence of the different vectors. They start getting away from each other. They start curving away, and the power of the signal is no longer effective. Okay, it can no longer. That's why we count on Fresnel zone for point-to-point microwave communications. Okay, we can never account on Fraunhofer zone. This is what we call, by the way, the far field area of the antenna. Now, within Fresnel zone, let's say you have two microwaves communicating with each other at point-to-point. What would be the radius of the Fresnel zone? So let's say you have a distance between these two microwaves, D, capital D. You have D1 here, D2 here. Okay, by selecting, you know, a random point at the middle of a semi-major axis of the ellipse. By the way, this is an ellipse. So the radius R is equal to lambda, which is the wavelength, times D1 times D2. This is D1. Yeah, R max is the one that we're calculating. The maximum radius is D1 times D2 times lambda, which is the wavelength, divided by D1 plus D2. Okay? This is how we measure the maximum radius. That's interesting. Okay? By the way, the maximum radius is, you know, the trough of the ellipse. Perhaps, you know, the trough is not the accurate word to say, but this is the lowest point at the bottom of the belly of the ellipse between these two microwave points. So again, R max is equal to lambda D1 D2 over D1 plus D2, lambda being the wavelengths. Okay, now antenna design. So many factors come into play when designing an antenna for a specific purpose, and they play an essential role in establishing a successful connectivity between the transmitter and the receiver. First of all, you have the distance at which the receiver is located. It is important to understand the potential distance of the receiver from the transmitter to adjust the transmit power so that the received gain would be guaranteed, would be effective at the other end of the communication system. So we take into note also that different types of antennas have different sensitivity toward the transmitter. That's why, by the way, for microwave communications, the best design for an antenna would be a dish antenna, a parabolic one. Why? Because it has a higher area which can focus the received signal to the receptor. Okay, and this increased, or this large area, this larger surface can increase the received gain of the signal. Second, geological and geolocation attributes. This entails understanding the characteristics of the path or the terrain, such as weather and geological conditions. This includes actually a study of the density of the obstacles, like, if you will, the meteo factors, weather factors, or trees, their thickness in order to decide the height of the emitting antenna, and the power needed to overcome different attenuation parameters or attenuation factors. Third, the operational wavelengths. This parameter influences the decision on how much power the antenna has to radiate in order to have the minimum attenuation while reducing the noise element. You know, because higher frequencies can carry higher capacity or larger amounts of data, but at the same time, higher frequencies have, if you will, a higher rate of attenuation within the atmosphere. That's where the problem is. Plus, higher frequencies, okay, although they carry a larger amount of information, the signal to noise ratio, it would be lower. Why? Because they are more susceptible to noise, more susceptible to interference due to the large amount of symbols that they carry within. So, as most of you are familiar with the concept, the quality of transmission is Q equal S over N, or SNR, signal to noise ratio, which is the difference or the ratio between the power of the clean signal divided by the power of the noise signal. Q needs to have a higher value for an adequate and acceptable transmission. All right, so this parameter influences the decision on how much power the antennas have to radiate with that order. Okay? Going back to explaining and breaking down the definition of the radiation pattern. So we've already seen and described how the radiation beam of an antenna breaks down to three lobes: the primary, main lobe, where most of the radiated power is located, and it points toward the main transmission direction. The side lobes, which are considered a waste of energy, should be as minimum as possible, and the back lobe, also another form of wasted energy, except that they point in the opposite direction. Both the sides and the back lobes are actually a type of waste, but also can have damaging effects, interfering with other stations as well. They are not part of the main direction of transmission. Radiation pattern. For the radiation pattern, we actually have two of them that need to be studied. Horizontal radiation pattern, which is actually the variation of the electrical field intensity on the horizontal plane, that allows us to measure the azimuth angle, which is the horizontal angle enclosing the main two edges of the beam, or the main lobe, the primary lobe in such case, on the horizontal plane. In other words, that would be the shape of the beam if we were looking downward. Let's say we are flying with a drone and we can actually see the main lobe, the primary lobe. This is what the primary lobe would look like from above, and that would be the horizontal angle of the opening of this primary lobe. Now, for the vertical radiation pattern, that is the variation of the electrical field intensity on the vertical plane, meaning that here we are measuring the zenith, or the vertical angle, from the ground up, okay, over the vertical plane, which is the angular spread of the two edges in the vertical direction. That would be the shape of the signal, or the main lobe, if we were looking at it sideways, meaning that if we were standing on the ground and looking at it, this would be the angle vertically of the beam and its shape from a vertical point of view. Okay? Now, of course, here they look very similar, you know, but the horizontal one is the horizontal spread, the vertical one is the vertical spread. That's the main difference between both. Directivity again. As a review, the directivity of the antenna is the concentration of the signal's power in a specific direction. It is measuring by how many steps the signal's intensity of a directed beam outshoots that of an isotropic beam projecting from a theoretical omnidirectional antenna operating at the same power of the directive one, within the same frequency range, and in the same transmission conditions, which includes same temperature, same air pressure, and other weather factors. Insertion impedance. Now, access or insertion impedance is a complex value that has one real part to it, which is the pure resistance here, and another imaginary part, which is the reactance. Again, the impedance is another word for resistance, electrical resistance value. However, when we're talking about high frequency components, we no longer only address the resistance part, because the resistance becomes very complex, that you need to address, you know, a more complex term, which is the impedance. The impedance is actually equal to the resistance, which is the pure value of this complex number, plus J multiplied by the reactance, which is the imaginary part of this number. The resistance, being a constant factor, has no effect on altering the impedance, but rather the reactance would. Okay, Why? Because the reactance, which is the imaginary part of this number, has a direct relationship to the frequency of the signal. Meaning that when we're talking about the reactance of a capacitor, Xc is equal to 1 over 2 pi Fc, which means that the frequency would affect also the value of the capacitor, okay? Or the reactance, the change of the reactance has a direct impact on the value of the frequency, and at the same time, or inversely, the frequency of the signal would affect also what the value of the reactance. So the imaginary part of the resistance would be changed or altered by the value of the frequency. So it would no longer be adapted at the entrance. Why? Because we need that the cable and the connector both having the same impedance, which is called the characteristic impedance, so as to have a perfect fit and to avoid having a wasted thermal energy. So a disparity between that value, which is the entrance impedance, and the impedance of the connection cable, results in what we call VSWR. What is VSWR? VSWR is variable standing wave ratio, where a part of the signal is being reflected off from the antenna's connector back to the cable and it interferes with the incoming signal. This is what we call variable standing wave ratio. The two signals, interfere against each other. This return signal will interfere with the incident signal, creating noise in the transmission. That's the main problem. Not to mention also, if you have a change of impedance, this will cause a heat problem, which will also create what is called the noise power, or power, a parasitical signal coming from the thermal energy altering the values of different electronic components and creating an interfering signal, a parasitic signal. We will talk more about that. So here we note that the characteristic impedance for communication devices between cables and connectors is usually normalized to Zc is equal to 50 ohms. Efficacity ratio, another antenna parameter. So efficacity is the measurement of how much power is being utilized by the antenna versus how much is being fed. Okay, through this parameter, we can find how much is being wasted due to, different imperfections within the antenna. So through experiments and observation, we noticed that this ratio could attain 90% for very high frequencies, the utilization factor for the antenna area. But for lower frequencies, it's limited to tens of percents. Okay, for some reason, high frequencies utilize the surface of the antenna much better than lower frequencies. Efficacity is also described as the radiation resistance divided over the radiation resistance plus the wasted radiation. Okay, so in other words, EPTA, which is efficacity ratio, is equal to radiation resistance divided by radiation resistance plus wasted radiation. Okay? Poynting vector. Okay, what's the definition of a Poynting vector? A wave traveling in a specific axis direction and oscillating in a plane normal to that axis, okay, carries with it a physical energy called the spectral density of flux, or Poynting vector. So Poynting vector is the spectral density of the flux of the electromagnetic wave being propagated, being radiated. This parameter represents the density of energy of an electromagnetic wave going with a normal angle through a virtual window area, going with a normal angle through a virtual window area of 1 meter squares during 1 second. So let's back up a little bit. This parameter, which is the Poynting vector, actually represents the density of energy of an electromagnetic wave with a normal angle, meaning it's hitting a virtual surface of 1 meter square with a normal angle to it, during 1 second lapse of time. So during this 1 second, how much of that flux penetrates a virtual 1 meter square area? This is the Poynting vector. Okay, so let's look at its equation. So the calculation actually came for the Poynting vector came from resolving the energy vector through Maxwell's equations. So you have E here is the electrical field intensity, epsilon 0 is empty space permittivity, B is the intensity of the magnetic field, mu 0 is the permeability, and URT is actually the power vector for that Poynting vector, okay, which is the density, physical energy called spectral density of flux. In other words, that's the density of flux, if you will, to make it in smaller terms. But let's go to the main equation that we came up with. And by the way, here we have the values for epsilon 0 and mu 0. So the Poynting vector, which is pi, this is capital pi. It's not actually, the pi of the circle, 3.14. That's actually another pi representing the Poynting vector. Pi RT is equal to E, and this is the rotational, multiplication with B, okay? Vectorial product between two vectors divided by mu 0. Okay, to get the flux of this vector traversing an area, we need to integrate pi through that area, the S or the A, if you will. What we get from that is pi equal E effective, or which is, the effective intensity of the electrical field. By the way, effective value of the intensity of the electrical field is E max, which is the maximum intensity of E vector divided by square 2. Okay, so Poynting vector is equal to effective intensity, electrical intensity, or electrical field intensity squared, divided by 120 times pi, which is pi equals 3.14. Okay, so again, Poynting vector is equal to effective electrical field intensity squared divided by 120 pi. Now, from that, we can actually measure the received power for a signal. Okay, the received power by an antenna. So PR is equal to Poynting vector times the effective surface that's being multiplied with the Poynting vector. Okay, the effective area of the surface. For parabolic dish antennas, the gain is G equal 4 pi effective surface divided by lambda square is equal 4 pi. By the way, effective surface is the geometric surface or geometric area of the of the antenna. Here we are considering a dish antenna, or not necessarily parabolic, but it's working, it draws its effectiveness or its operation through its area, not its length. So G equal 4 pi S effective divided by lambda square, which is the effective surface is equal to geometric surface times nu. Nu is the utilization factor of the area of the antenna. Okay, again, as we mentioned before, this is depending on different factors such as the manufacturing and other things. Effective length for linear antennas. So this parameter pertains to linear antennas and microstrip antennas, which are the printed circuits antennas, if you are familiar with, that are linear. For microstrip, they can be linear but folded, in a spiral shape, but they are printed antennas. Okay, that's why it was no longer needed for you to carry a mobile phone with an antenna that needs to be stretched outwardly. No, they are printed and folded on the inside. So they operate through their lens, as we mentioned. For such an antenna to generate a maximum radiation, the feeder needs to be installed in the middle of this lens, okay, of this antenna linear form. And this lens value has to be equal to half of the wavelength being radiated, by the way. which means 2L is equal lambda over 2, 2L being the length, half of the length of the antenna to the left and another half to the right, okay? L being one breadth from the center where the feeder is connected to the edge. And thus LE, effective length of the antenna, is equal to over pi L, all right? Noise temperature and power. Now, this is a serious factor affecting the receiving end. High temperatures due to weather or active components of a communication device affect the electronic components of the internal circuitry and alters their values. For instance, if you consider the impedance of a capacitor, it has a real part and an imaginary part. Again, the real part is not very relevant, but the imaginary part, as you see, it is correlated with the frequency value. So for a different frequency, you would have a different impedance. It would actually like virtually change the factor, but not only that, even a higher temperature, okay, would change the C value, which is the capacitance, the capacity value of the capacitor, okay, in farads. This will also lead to the change of the frequency that's being generated, and it can actually create a parasitical signal, which is what we call a noisy frequency, a noise signal, interfering with the main signal. So as we see in the upper equation, the value of reactance affects the frequency of the signal, right? A high temperature can dilate the component, impacting the frequency value of the signal. Now, not only that, this will lead to a noise signal that can affect the signal to noise ratio, SNR, degrading the reception quality. The power of such noise signal induced by a high temperature, by a heating of the receiving electronic components and device within the receiver, this power is equal to K times Tn times delta F or W. Okay, P is the power of the noisy signal. Okay, Berwi means noise, by the way. So P is the power of this parasitical signal that was created due to the temperature, is equal to K, which is Boltzmann constant, is equal to 1.38 times 10 to the power minus 23 watt by Hertz by Kelvin, times the temperature, which is the temperature in Kelvin. Tn is equal to the temperature of the device in Celsius plus 273, plus delta F, which is also what? This is the bandwidth. Now, also the bandwidth contributes to having a higher noise factor, okay? When you're using a larger bandwidth, it would also affect a, the noise signal, creating a higher noise power. So again, as we've observed, the Poynting vector is expressed in relationship to the electrical fields. So capital Pi is equal to effective electrical field intensity squared divided by 120 pi. To put that in another way, the Poynting vector is the intensity of the flux of the signal, right, per unit area. So we can also replace it by what? By the transmitted power, right, divided by the area where that power is being going through, is being transmitted, or the power that is being traveled, the area where that power is traveling and penetrating that area. That's another definition. It's a similar definition of E effective square over 120 pi. So again, the Poynting vector, since it's the intensity of the flux of the signal, which is the transmitted power per area unit, which is 4 pi r square. By the way, 4 pi r square is the surface of a sphere, okay, because the lobe has a form of a sphere. So putting these two equations side by side, we get effective electrical field intensity equals square root to 30 times transmitted power divided by the radius of the area being covered. And this is expressed in volt per meter over meter, okay, per meter to the power -1, in other words. So radiation power, as we noticed that in the last formula, the field intensity is inversely proportional to the coverage radius, which makes sense since the flux being distributed on a larger radius, larger area, will become weaker per unit of square meters. Meanwhile, having a narrower beam will focus the spectral density in a smaller area, making it stronger. So this leads to a more intense radiated power and a sharper electrical field like a laser beam. So effective intensity of the electrical field is equal to square root 30 times transmitted power divided by the radius of the coverage area expressed in volt per meter. We can learn that the value of intensity, E effective over a radius of coverage R, from the transmitter using the following equation. Effective E is equal square root to 30 transmitted power times the directivity, because it's in direct relationship to the concentrated wave within a directive antenna divided by the radius. By the way, another example for that, it's like you have a limited amount of pepper or salt that you are distributing on a small plate versus a very large plate. The very larger plate would get a smaller amount of salt. That's the same concept playing over here. By observing the below chart, we see how the Poynting vector value decreases with the increase of the coverage area. So for a very small area, the P, or transmitted power of the Poynting vector, would be much stronger than for a larger radius. For a longer or larger radius and larger area, longer radius, you would get almost zero Poynting vector, okay, due to the dispersion of the power over a very large surface. Bandwidth, which is delta F. Now, another antenna parameter is the bandwidth, which is the frequency interval of operation for the signal, for the antenna, for which the gain is the strongest. Outside that interval, the frequencies are intentionally lowered down. They are intentionally choked to maximize the power for the main band and to reduce interference against other operating antennas in the environment. A larger bandwidth is available when using shorter waves and very or ultra high frequencies, of course, providing the possibility to modulate higher data rates, as we mentioned before. But opposite to that, longer waves provide smaller bands. Mathematically speaking, delta F is the difference between the upper and lower frequencies, F1 and F2, for which the gain curve would be at a value of maximum gain minus 3 decibels. Okay, so where the signal is at the value equal to maximum gain minus 3 decibels, that's where you draw a line, and where the line cuts within the frequency band, these two intersecting points would represent the upper and lower frequencies. The difference between both would represent or would give you the bandwidth of operation for such an antenna. At this level, the gain is at 70% of its maximum power. That's the bandwidth. Electrical communications equation. So let's start by considering the source emitter being an isotropic one. The wave power distributed all over the isotropic sphere is expressed by emitted power divided by 4 pi r square. This is actually, again, the area of a sphere from the outside. That's why 4 pi r square. That's the area of the surface of the external sphere, the skin of a ball, if you will. The power absorbed by a receiving antenna having an area surface SR is expressed by PR is equal to effective power times the receiving surface or area of the antenna divided by 4 pi r square. Of course, practically, we are more interested in designing an antenna that is directed rather than isotropic, focusing the energy of the wave in a defined direction so that the received power will also depend in such case on the directivity gain GE belonging to the emitting antenna. Hence, the equation of the received power is equal to PR equal PE, emitted power times emitted gain of the transmitter, or the gain of directivity gain of the transmitter times the surface of the receptor divided by 4 pi r square. However, this equation does not explicitly reveal a relationship with the wavelengths, so let's try to derive that from the equation of gain expressed in terms of lambda and directivity. So G equal 4 pi effective surface, which is the effective area of the antenna, divided by lambda squared. So the effective surface is equal to directivity gain times lambda squared divided by 4 pi. You replace that into the first equation, so you get PR, received power, is equal PE GE GR over 4 pi D divided by lambda squared. So D is the same as R, okay, the radius. So the received power is equal to the emitted power times emitted gain, which is the transmitting antenna directivity, times the receiving antenna gain, times c square, which is the speed of light squared, divided by 4 pi squared times d squared times frequency squared. D, of course, being what? Being the radius of the antenna. Transmitter circuit. Now, the source signal, LF or low frequency signal, which is the audio, here we're going to take into account, or we're going to consider the example of the amplitude modulation for AM radio bands, AM frequencies. So for an AM radio, what we have is a low frequency signal, LF, coming from an audio microphone here. Okay, it goes through an amplifier, which is a low frequency amplifier, and then inserted into the modulator, which is a multiplicator circuit, by the way. The other input of that modulator is a high frequency carrier, which is, you know, in the 100 megahertz range. So it is a high frequency signal that's also amplified using its own specific HF amplifier. After that, the modulator, you know, you have a multiplication of both signals, and then the modulated signal would be amplified using a power amplifier, for the modulated signal before transmitting it to the antenna. Now, of course, the antenna converts the electrical signal into an electromagnetic wave having two vectors normal to each other, E electrical field vector and M magnetic field vector. Okay, mathematically speaking, this is what is happening within the modulator. So MT is actually the equation of the audio signal that needs to be transmitted and to be carried over a higher frequency. It has the form of AM, which is the amplitude of the audio, times cosine omega MT, omega being the pulsation, which is 2 pi FM. 2 pi times the frequency of the signal of the message. CT is the carrier equation, which is equal to AC, amplitude of the carrier signal, the high frequency signal, times cosine omega CT, omega C being 2 pi FC, FC being the frequency of the carrier signal, of the carrier wave. So the multiplicator multiplies both signals. What we get is AM AC divided by 2. That is the equation of the modulated signal, by the way. Cosine 2 pi FC plus FM times cosine, actually here is a plus cosine 2 pi FC minus FM. Okay, this is what we get. So here it's actually a plus, not a multiplication. This is deriving from trigonometry equations. Okay, when we multiply cosine by cosine, what you get is 1/2 AM AC times cosine Fm, okay, cosine omega m plus omega c plus cosine omega m minus omega c, okay, or vice versa, omega c minus omega m. This is how we got the modulated signal. As you see, the message is actually hidden within the envelope of the carrier as a result for that modulation. So here's the message. It is hidden within the envelope or the external shape of the carrier. This is how, of course, on the other end, the demodulator needs to extract this message using a special circuitry to retrieve the audio signal that's being transmitted. Dish antenna parabolic section. Mathematically speaking, the parabola is a conic section that resides in a plane parallel to the directress D. We notice that no matter where a random M point is located on the parabola, it's always at an equal distance from the foci, the focal point of the parabola, and the normal projection over the directress marked as H. So always MH is equal to MF. Another, main equation for the parabola is y squared is equal to pi x when, it's pointing left, right, or x squared equal to pi y when the parabola is either pointing upwards or downwards. Okay, this is the main equation. Now, that's the full equation of the parabola. X minus h squared is equal 4 pi y minus k. Okay, h and k are actually the coordinates of the vertex, the first vertex of the parabola. Here they are both zeros because it is at the center of the axis, at the origin point rather. Okay, as the foci is equal to k plus p. Okay, now p, you can measure it based on the equation, okay, by replacement of different parameters. Okay, so here in such case, let's say x squared is equal to 2y. Okay, so p 4p is equal to 2, p equal 2 also. So the focal point is equal to k plus p, which is 0 plus 2. That's the foci of the parabola. Okay, and the directress is equal to k minus p, which is located 2 squares below. Okay, that's the directress, which defines, if you will, the heading. Okay, so the normal axis to the directress would define where the parabola is pointing. This is the equation, or this is the representation of the dish antenna, the parabole of its its curvature. Advantages of dish antennas. So for receiver antennas, the directed wave vectors traveling parallel to each other, here in the second visualization, when they are received by the parabolic surface, they are reflected and back to the receiver, of course, but they travel the same distance here, so they arrive at phase to the receptor. Okay, that's why there's no phase difference between them, which helps amplifying the received signal as long as you have a larger area for the receiving dish antenna. In the same manner, from a transmitter point of view, which is the first image here, the rays emitted by the transponder are reflected back by the antenna in a parallel manner. Okay, they are parallel to each other and to the main direction of the signal, the main axis, which focuses this entire signal, all these wave vectors, in a parallel form back to the other point, the other receiving point. Okay, and all of them being in phase, of course. Another thing that we might have skipped, that one of the main advantages for a dish antenna is that the waves are summed up in the receiving direction. They are added together to the receiver, which amplifies the received signal. Now, considering the gain again, so again, the gain is equal to, which is also the gain of reception, the gain of received signal in decibels. So it is 4 pi geometric surface times nu, which is the effective surface, of course, divided by lambda square. Again, when you have a larger surface, you have a higher receptivity of the signal, a higher gain of reception. Microwave communications. For microwave communications, you have 3 types of waves that are received by the other end. First of all, the direct waves. These are what we account for the most. Direct waves, actually, these are the ones that we consider for an effective communication. They are the ones traveling directly from the sending end to the receiving end in a parallel form to the ground. All right? But another part of these waves are scattered as spatial waves and terrestrial waves that we're gonna address. Now, by the way, again, this direct waves, okay, is where 80% of the main power resides, which is the Fresnel zone. This needs to be completely cleared from any obstacle or any form of barrier so as to provide a very effective transmission without an attenuation from, surrounding objects. Terrestrial waves, another part of the waves hits the ground and is reflected back to the receiver. This is what we call terrestrial waves. The problem is that these waves follow a path having a different length than the direct path. As a result for that, they arrive out of phase with the direct waves, causing interference with them. Why? Because they are added up to the direct waves, however, they are out of phase. So they don't actually add up to them. They mix up with them, but most of them would be destructive due to that phase shift. Finally, spatial waves are the waves sent back from the atmosphere, specifically due to refraction, to the changing refraction index as you go up in the atmosphere. They are sent back, they refract to a certain point, and then they are sent back to the receiver, also interfering with the direct waves. Impact of the atmosphere on radio transmission. Now, the atmosphere has multiple damaging effects on a radio wave. One of them is the attenuation we formerly talked about, but more than that, the refraction index that changes due to temperature, humidity, and air pressure with the altitude also affects the direction of the wave even more dramatically. So, within this graph, we notice observing this illustration that higher altitudes would result in a reduction or a weaker refraction index until it nearly approaches zero. So for lower altitudes, you have a higher refraction index on the x-axis and vice versa. In other words, for higher altitudes, the signal becomes to reflect way more than refract, because refractive index is almost the inverse of a reflection index. This explains how the spatial waves are sent back from upper atmospheric layers back to the receiver. Okay, that's the problem with them. Microwave transmission system main parts. Okay, the antenna architecture. So this transmission system is made of few main parts. First of all, you have the internal unit that has the modulation circuitry in it. It transforms the baseband signal, which is, the sequence of bits, zeros and one that were, shaped as or modulated in NRZ, and now returned to zero, but they are mainly baseband. Okay, these signals are modulated into what is called an intermediate frequency signal, which is basically a phase shift keying modulation before, in order to transmit the signal into the cable connecting that unit back to the external unit, which is the assembly of antenna, transmitter, and the modulator also, which is at the back of the antenna. The external unit has the radio transmission system in it, the antenna, of course, also connected to it. The former, which is the transmission system, remodulates the intermediate frequency signal into a high frequency signal. It is also being fed by power from this internal unit. So the internal unit sends also power, not only the modulated intermediate frequency within the cable that connects both the internal unit to the external unit. Okay, in reverse, the incoming signal that's received by the external unit is transformed into a high frequency RF current that then it is demodulated to an intermediate frequency signal by the radio transmission system, which is at the back of the microwave dish. After that, when it arrives to the internal unit, it is demodulated again as a baseband signal that, that is the same sequence of bits or the same signal that is sent and received by a network switch. Okay, so this is the signal that carries, explicit series of zeros and one. Microwave design. Microwave communications are the transmission of data and voice using short electromagnetic waves or high frequency waves, ranging usually from 300 megahertz to 300 gigahertz, or from 1 meter waves to 1 millimeter waves. This design is used for point-to-point communication to relay massive data between stations, not to directly communicate with users. The sectorial antennas transmit and receive communications from mobile subscribers in the mobile scenario. All of these communications are then aggregated, summed up. Now, they are modulated in channels and then over a higher frequency to be transmitted to a distance station via the microwave link. The common bands of operation are 2.4 gigahertz, 5 all the way to 18 gigahertz. A very important criteria for microwave communications is the line of sight. Line of sight is actually the direct path where the Fresnel zone exists between the 2 points. It should be cleared from any obstacle because it has 80% of the power of the transmitted wave. So in other words, the 2 microwave points should be visible to each other without any blockage. Even a tree can actually block the communication in such case when talking about millimetric waves. Alignment. The 2 antennas facing each other between both sides should be perfectly aligned, that a virtual direct line going from the center of the first one should intersect with the center of the second antenna, the center of the second dish, if you will. Okay, so as to have a clear, and an effective communication. Now, this alignment is done using spectrography, not actually a carrier spectrum analyzer or a voltmeter to measure the power of the signal that is being received. Another thing, it is highly directional, meaning that the directivity of both antennas should be very large as to shape to projected beam into a tubular narrow cylinder, focusing the power of the surface of the second receiving antenna. That's one reason why we use higher frequencies, giving their proportionality to directivity. So higher frequencies come along with a highly directional beam, meaning that the beam is focused and there is no waste. The focus of the beam would be narrowed down to the area of the receiving antenna on the other end, which is very important, so as to reduce any wasted energy from the scattered lobes, right? So this is a very important criteria. Again, in order to align both antennas, first of all, we start visually, then you can use a voltmeter to measure the power of the signals that's being received on the other end. It needs to have a specific value based on the design criteria, or you can measure or confirm the alignment using a spectrum analyzer so as to detect the power of the received frequency on the other end to confirm that both antennas are facing each other perfectly. To overcome this hurdle, one clever technique is adopted to tilt the other antenna, the receiving antenna of the next station, a little upward to drive its normal axis away from the alternative path to avoid the reception of the alternative wave, so to speak, of course at the account of losing some of the transmitted power. However, the path of the alternative reflected signal from the ground or from the water body is deflected from the antenna dish, which no longer receives it in a way that can interfere with the main incoming signal. This is one way to look at it. Another way to do it is actually to mount the microwave right before a peak of a mountain, a hill or something. That hill would block partially or completely even the alternative waves that are being reflected by a lower surface. This way, this antenna can be guaranteed to only receive the main signal from the line of sight of connecting both antennas, the transmitter and the receiver, while blocking the alternative path of the waves that are reflected from the ground, which are called, by the way, also terrestrial waves. ATPC, Automatic Transmission Power Control. ATPC is an automated or automatic mechanism within the transmission system of the microwave that adjusts the power, the transmitted power dynamically based on the measurements of the received signal on the other end sent back by the feedback channel. By the way, for two microwave points, you have two frequencies in play. The transmit for each point, the transmit wave and the receiving wave, the transmit frequency and the receiving frequency. There must be a difference between the two to avoid interference, which is called TR spacing, which is transmit, receive, spacing. Okay, usually it's a band of 500 megahertz, around that value. When the received signal on the other end is low, ATPC increases gradually the power of the transmitter to cope with the loss of power due to absorption within the atmosphere, due to attenuation rather, along with along the communications path. And if the power is too high, it dynamically lowers the transmit power so as to keep this level around -40 decibel, which is an effective value. Now you would think that it's a negative value. Actually, this is because we are using the logarithmic scale. Being negative on the log scale does not mean that it's actually negative, but it's lower than a specific threshold. Still positive though. Why ATPC? Due to the changing weather conditions, the transmit power of a microwave needs to be changed dynamically, given that heavy rains will cause a high attenuation requiring an upward adjustment of the transmit power, but a clear weather has a minimal free space loss attenuation requiring a lower transmit power that is needed. But why not keep the transmit power at its maximum? Again, as we mentioned, bad weather conditions involving fog, heavy clouds, high humidity, rain, and heavy rain cause an attenuation of the main signal, which leads to low receptivity at the other end and a higher BER or bit error rate, resulting in a bad communication. In such case, the system needs to automatically adjust the power of the transmitter upwards to overcome this dip in the signal. Now, interference needs to be in check. So the power increases. If unchecked and unbalanced, it has its own lows as well. It has its own disadvantages. Why? For instance, rain not only attenuates the signal, but water droplets, being a good conductor of electricity, act as a dipole omnidirectional antenna. So due to the inducted current caused by the incoming electromagnetic waves, it acts as an antenna, transmitting the same frequency in all directions, which interferes with the incoming signal. That's one reason to keep the adjustment moderate, not to increase the power of the transmission indefinitely. Power consumption. Now, high transmit power leads also to higher demands on electrical energy, and this will add to the overall operational cost of the network, or OPEX. So power should be adjusted as needed only. Second, receiver damage. Actually, this is perhaps the third or the fourth point. But receiver damage. The receiver has a limited tolerance to the received signal power. Despite the need for that power to be adequate, it cannot be indefinitely high because it can burn the receiver. This actually was witnessed with a microwave oven when someone forgets to place something within a microwave and runs it for a few minutes at high power. This breaks the transmitter because of the absence of food and water where the power can dissipate rather than be reflected back to the transmitter, which damages and can even burn the transmitter and breaks the microwave. Also, noise factor. Excessively high power signal causes the heating of the receiver on the other end. This adds to the overall temperature of the receiving device. The high temperature, as discussed previously, is behind what is called noise temperature. It changes the reactive characteristics of the components and generates a parasitical noise signal that interferes with the main original signal, causing a high bit error rate. Also, another factor to be considered is the interference with other stations, especially belonging to other companies, other service providers. So another factor to take into account is other stations operating even if miles away using the same or close frequencies. If the transmitter is emitting higher amplitude waves, they can go further against other stations, causing interference and a degradation of their communications for other operators, which would cause you a legal problem, of course. Second parameter, which is the adaptive modulation that was introduced also to dynamically adapt the modulation based on the transmission scenario. Adaptive modulation is an automatic mechanism that triggers the change of modulation between different schemes based on the transmission scenario, affecting the signal-to-noise factor, SNR, or signal-to-noise ratio. For better weather conditions, AM switches to modulation schemes, providing a higher data output by encoding a larger number of symbols, while using both the amplitude and the phase to carry them, such as 16 quadrature amplitude modulation, 32, 64 to 56, all the way to 1024 to 1056 even, QAM. Meaning 2056 symbols that can be carried. But for worse weather conditions, the SNR degrades, which is detected by a higher bit error rate from the other end, sent by the feedback channel again. Once this is reported to the transmitting side, the modulator gradually switches to a lower capacity modulation, more immune against errors and interference. As an example, if it was at 256 QAM, it goes down to 256 QAM strong at first, which is, by the way, using still the same modulation scheme, but most of the symbols that are sent are actually protection symbols, okay? They are a redundancy for the information that's being sent. So it has a lower throughput because some of the bits are actually sent as a correction mechanism for the errors that might occur. Then to 64 QAM, each time measuring the BER, at its lowest, it goes to QPSK, meaning that when the weather conditions are horrible, QPSK is the most immune against errors. Why? Because it's modulating the symbols. It actually modulates 4 symbols, and using the phase without the amplitude, that is the most prone to the interference, because interference affects the amplitude, the envelope, more than the phase. And vice versa, as the transmission quality becomes better, the transmitter switches to higher capacity modulation schemes that have become more effective as the weather conditions became better. So microwave systems use different modulation schemes for different transmission scenarios. Let's list and understand these schemes and how they work. Let's start with QPSK, or quadrature phase shift keying. This modulation scheme changes the phase of the signal in a certain way to encode data within it without touching the amplitude. So it can harbor 4 different phase values and thus 4 binary symbols that can be encoded with it. Okay, with 4 symbols, this is how we can measure how many bits we can carry within each symbol. 2 to the power of n, because we have 2 values of bits, 2 possible values, either 0 or 1, okay? So 2 to the power of n, this is, by the way, a combination with repetition, is equal to 4 symbols. So if you use the logarithm, ln2 to the power of n equal ln2 to the power of 2, because 2 to the power of 2 is 4, okay? n ln2 is equal to ln2, so n equal to, you have 2 bits within each symbol. These are the different combinations that make 4 symbols. You have 0 0 at 45 degrees, which is, you know, the first phase, then 0 1, 1 0, and 1 1 at 4 circle. Yeah, this is the last phase value. We'll see it in the next image. You see here you have 4 symbols. This is the first symbol at pi over 4, which is 45 degrees from the original axis. As we notice looking at the figure to the bottom right, the amplitude of the signal is never touched because we're encoding the symbols by using only the phase changes, the angular changes without the amplitude. Alright, so we have 4 shifts. You have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Since this modulation is not touching the amplitude, it's more immune and resilient against interference, because usually interference affects the amplitude more than it affects the phase. By the way, the amplitude is the distance from the center of the trigonometric circle all the way to the circumference here. This is where the amplitude of the signal is this distance, this radius here. So the effects of fading are mitigated for such a modulation scheme more than QAM or other modulation schemes. As for 16 QAM or 64 QAM or QAM, so for 16 up to 1024, the modulation uses both phase and amplitude to encode symbols within the wave. As we go up in the modulation scheme, more symbols become crammed in a short time span within the signal, which means that they become more prone, more susceptible to fading, because if a fading occurs, it can kill with it 3 to 4 to 5 symbols instead of affecting one symbol that dips below the receiving threshold, right? And by the way, one reason to having bit error rates is that if you have a dip of amplitude while a symbol is, the value of the symbol is read through measuring the amplitude and the phase. So let's say 2 symbols have the same phase, like these 2 here, but different amplitudes. If for some reason a fading occurs, this symbol can be lowered, it can drop down to the level of the symbol on the same diagonal, okay? So the receiver would read them as being the same symbol, the same value, although this symbol is different than this one. However, due to the attenuation or to the dip, the fading dip that occurred, okay, it's considered to be the same symbol as this one. Why? Because it was read at the same amplitude. It fell to the same level of the other signal, okay, of the other symbol, sorry. That's why fading is very damaging to signals, and it can incur higher bit error rates. So for higher modulations, they are more susceptible to noise. That's why QAM modulation are best used for good weather conditions. And of course, there's a scale to that. So if the weather conditions are not as bad, okay, they can tolerate like using 16 QAM where the symbols are a little bit distant from each other, okay, in amplitude term. So even if this symbol dips a little bit, it can still be measured as this value, okay, given that it doesn't drop below half of the distance from this level here to the level of the signal or the symbol that is on the diagonal over here, okay? Because once it crosses half of the distance, it will be considered as being this value instead of this value, okay? And of course, the conditions that affect these transmissions are humidity, clouds, or bad weather conditions, heavy rains, etc. Okay, that's why QAM are preferred for calmer weather conditions, and when you don't have like any dust in the air also, but dust is not as damaging as water or precipitations within the atmosphere. Impedance adaptation. Now, in order to adapt the impedance, we need to take care of some parameters, especially the reflection coefficient. This parameter measures the percentage of the reflected power of the signal or the wave versus the full power during insertion of the signal via the connector from transmission cable to the antenna. So basically, this is the ratio between the power that has reflected back from the connector and is actually interfering with the incident signal versus the full power of the original impacting or incident signal. So beta, which is this parameter, is equal to ZL, line impedance minus Z0, which is the proper characteristic impedance of the transmission altogether, or ZC, in other words, divided by ZL plus Z0. ZL can be considered either the impedance of the transmission line compared to the proper characteristic impedance Z0. Observing the equation, we notice that in order to reduce, if not annihilate, the reflection, which is even better in the inverse direction from the cable, ZL has to be as close as possible to Z0, so as to have ZL minus Z0 equals 0, and then you would get a null reflection, a zero reflection. This would nullify the reflection value if ZL is equal to Z0, meaning no reflection occurs. Of course, it's not, or it's never perfect. You would still get some return, but we try to mitigate it as much as possible. Impedance adaptation part 2. So the input or insertion impedance of the antenna is given by the following equation: Zn equals Z0 times ZL plus JZ0 tangent or tan beta L divided by Z0 plus JZL tan beta L. Now, L is the distance from the load where we're measuring this, impedance, and beta is the propagation constant, which is equal to 2 pi divided by lambda, lambda being the wavelengths. Another parameter is VSWR, or variable standing wave ratio. VSWR is the ratio of the maximum to minimum voltage on a transmission line, which changes due to the presence of standing waves due to a backward reflection from the connector. So basically, you have VSWR is the difference or the ratio between the maximum value, the maximum of a wavelength, divided by the minimum of that wavelength, and the perfect condition is for us to have a VSWR that is 1, okay? A perfect ratio between a maximum and a minimum. So, meaning that the minimum peak is equal to the maximum peak, and there's no weakening of the signal due to a standing wave that is being reflected from the other side of the connector. VSWR is also a factor related to the reflection coefficient, through the following equation, which is VSWR is equal to 1 plus gamma divided by 1 minus gamma. When you have zero reflection, you would get a perfect VSWR, which is equal to 1. Of course, you can never get a perfect one, but you can get as close as possible when you have a minimum reflection coefficient, which is around 0.95% based on the manufacturing perfection based on different other parameters, concerning the connector and the transmission line itself. Free space loss. Now, free space loss is a parameter between two antennas, given that we're not accounting for any obvious obstacles. It is the loss of the power of the signal within a free space. A, which is the free space loss, is equal to 92.4 plus 20 log D, D being the distance between the 2 points of the microwave link in meters, and frequency F is in gigahertz. So A equal 92.4 plus 20 log D plus 20 log F. Of course, not taking into account the gain of augmentation of the signal at the transmit point, or the gain of augmentation of the signal at the receiving point. So this calculation, this measurement, is right after the first microwave point and right before the receiving microwave point through the microwave link. It pertains only to the space between the two. Of course, before that you have a transmit power, which is increased by the gain of directivity at the first point, and then the receiving power increased by the gain of receptivity of the second point. Also, there would be a fading margin here, which is not accounted for this calculation. Second, the microwave antenna gain pertaining to microwaves. So again, the gain is the difference between a directive antenna and an isotropic antenna transmitting at the same frequency using the same power and through the same conditions of transmissions, which are the same temperature, humidity, and air pressure. Okay, so Pi, the power for a directive antenna, over the P of an isotropic antenna, which is the power of an isotropic one, theoretical antenna, is equal to pi times d, which is the directivity, gain of directivity, divided by the wavelengths squared. Also another parameter, which is the half power angle, or the angle of the beam at half power. This is where the points intersect with the beam where the power decreases by a half, or 3 decibels on both sides of the beam. So theta 0.5 or half power angle is around 65 degrees to 70 degrees times lambda over d. Lambda is the wavelengths in meters, of course, and d is the directivity in decibels. Okay, thank you for watching and see you in another video.